Hello, everyone. My name is Cornelia Davis, and I'm a technology fellow here at Spectro Cloud. What I want to talk to you about today is local AI. If you don't know what that is, don't worry. I'll tell you more about that in a moment. But in addition to learning about local AI, we're also going to learn a little bit about ChatGPT and the ChatGPT API, and a little bit about how AI models work in general. Now you'll see here that it says it's a beginner's tour, so things are going to stay at a fairly high level. But I am betting that many of you are like I was just a few months ago, where, yeah, we had played with ChatGPT, but we didn't really understand the details of what was going on under the covers. So I'm going to pull back the first layer. So I'm going to start off with the vanity slide. You can see here the star history of this local AI open source project. So that's the first thing. Local AI is an open source project that you can find here at the URL that you see on the screen. And yes, it just started in March of this year, and here we are in September, and you can see the growth has been pretty significant. That really indicates not only something about the quality of the software that's in that open source project, but about a need that is there. Now, what exactly does this open source project do, local AI? Well, here's exactly what it says on the local AI website. Local AI is the free open source AI alternative. Open source, open AI alternative. So OpenAI, as you know, is what's behind ChatGPT. And what local AI does is it acts as a drop-in replacement for the REST API. So when you go to chat with ChatGPT and you're in the web interface, of course, behind that, when you type in a question, it fires off a request to some API that's sitting up in the cloud. What local AI does is it mirrors, it replicates that API, but with a different implementation at the back end. So it's compatible with OpenAI API specifications for local inferencing. My goodness, what does that mean? It allows you to run LLMs and a few other things, generate images, audio, the things that OpenAI supports through their APIs, either locally or on-prem with consumer-grade hardware, supporting multiple model families that are compatible with the GGML format. I'll say more about that format in just a moment. It does not require a GPU. So that's a mouthful, but I'm going to draw out a number of things that I've bolded here. These are the things that we're going to drill into about local AI and about AI in general. We'll talk a little bit about the REST API and how that's structured in local AI. We will talk about local inferencing. What does that mean? What does it mean to do inferencing local versus somewhere else, presumably in the cloud? Of course, we're going to spend some time with ChatGPT, and we'll spend some time with one of the APIs that are there. And then we'll talk a little bit about models. Models, if you will, are the workloads, the AI workloads. And so we'll talk a little bit about these models and model families. So let's start here. I am sure that virtually all of you have done this. You've gone to ChatGPT and you've asked a question. Let's say, what characterizes Impressionist art? And we'll do a little live demo in just a bit. And you get back an answer. So, of course, you're making that request to a website. And I alluded earlier that that website is making a request, an API request to an OpenAI API. And that API is sitting up in the cloud somewhere. That's ChatGPT sitting in the cloud. And of course, in there, there's some running code. So that request comes in, and then there's some running code, and you get back a response, and then that response is displayed. We'll dig into it a little bit to see what that API looks like. I'll hint, it's called the completion API, and I'll explain that more in just a bit. Now, if we just click down one level on this, what we see is, of course, there's an API. That's the request is sent to that API. And then that API is invoking the LLM. It's invoking the large language model. So we'll talk about what those large language models look like. We'll kind of break those apart and look at the structure of those in just a moment. What local AI does is it says, rather than being required to run those things up in the cloud, specifically going to the OpenAI endpoint, what we're going to be able to do is we're going to be able to run those language models through an OpenAI compatible API on your own hardware. Now, I'm going to do something in this talk that's a little uncharacteristic. I'm not going to talk about the use cases to start. I'm going to go into the implementation in a little bit of detail, and then we'll circle back on some of the use cases, because I think once we dig under the covers just a little bit, those use cases are going to resonate, and you're going to see why these things are more important. So I promise we'll get back to use cases at the end. So before moving on, I want to point out one slight change that I just made on that slide. You might remember that the big blue box on the right-hand side used to say LLMs, and I changed it to say a language model. Now, the reason I did that is because large language models really are large, and you'll see where that size comes in just a moment when I break down what those models look like. Of course, running on local hardware, you might not have, well, you're not going to have the same amount of space that you would have on big, beefy machines running in the cloud. So it's arguable whether you would say that those things that are running, let's say on my MacBook Pro here, which I'm going to show you in just a moment, are really large language models. And so we can debate that, although we're not going to debate that today. But to drill in on that point just a little bit, I want to show you these things side by side. So ChatGPT, so GPT 3.5, which is the model that when you go to ChatGPT, unless you've got a subscription where you're using the latest model, which is 4.0, if you're just using it as a regular consumer, most of the people, the model that is being run at the back end, so it goes to the API and then it runs a large language model. The version of that large language model is GPT 3.5. What you can see there is that it has 175 billion parameters. Now, I'll explain what these parameters are in just a moment. You can think of it just like you normally think of any parameters. It's just an input. It's a number of inputs that are coming in, and you'll see what those inputs are in just a bit. Now, in terms of those inputs, the file size of that, and by the way, it's not just the file size, it's if you were to load all of those billion parameters into memory to be able to run that model, which is what you need to do, that would be about 700 gigabytes of storage. So whether it's file storage or memory storage, you need to load it into memory to run it. So you can see that there's no way that I could run something like that on my local laptop. Now, in just a bit, I'm going to demo this, and I'm going to show you I'm running a model called Llama. Llama is a model that came out of Meta, and that's one of the models that you could run locally. We'll talk more about that in just a bit. Now, how does the size compare? Well, instead of 175 billion parameters, so inputs that are coming in, instead, Llama has a model that is either 7 or 13 billion parameters. They have a couple of different versions of their model. And depending on some other characteristics, that means that the file size, because we're loading those things from a file, and of course the memory requirements range anywhere from about 3.5 to 25 gigabytes in size. So I'm probably not going to run the 25 gigabytes on my laptop here, because I think I have 32 gig of memory or something like that. But I might run the 3.5 or maybe a 10 gigabyte version of this model. So that just gives you an idea. Now, of course, the larger models are going to give you different results than the smaller models. And that's one of the things that you need to decide as you start rolling out your AI-based workloads. So there's a lot involved in deciding on the models and things like that. We're not going to cover a lot of that today, but I'll make a few more comments. So without further ado, let's just play a little bit. Let me show you some of the things that we've just been talking about in action. So the first thing that I want to do is I want to, first of all, here I'll show you is the localai.io is the website that you want to go to see all the documentation. We'll come back to this page in just a moment. But what I want to do here is start over here in ChatGPT. Now, the first thing I'm going to do is I'm going to use my sample query that I just showed you in the slide, and I'm going to say, what characterizes, let's see if I can type, Impressionist art. And it looks like I misspelled that. I will go ahead and correct that, although I think it would work anyway. So I asked the question and it says, hey, Impressionist art is characterized by several features. And then it goes on and on. So it's talking about light and color and outdoor scenes. And boy, that's more info than I wanted. So let me ask it to summarize that. So I can say, can you summarize that in 300 characters or less? Oh, I cannot type today. Let's correct that. And it says, sure, Impressionist art born in the late 19th century France emphasizes, and then it goes on to characterize that. It, of course, includes a number of notable artists like Monet and Renoir and Degas, which I've probably horribly mispronounced. Now, part of the reason that I'm interested in this is that I was one of the people who went to see the immersive Van Gogh experience. Super, super cool. In fact, I saw it a couple of times. So I'm thinking, well, why isn't Van Gogh on this list? And so I'll say something like, well, what about Van Gogh? And it says, while often associated with Impressionist, specifically post-Impressionist, he's not actually considered an Impressionist artist. Okay. So one of the first things that I want to point out to you here is that you'll notice that my subsequent queries there was some context that was assumed. So when I said, can you summarize that? I didn't say, can you tell me what characterizes Impressionist art in 300 characters or less? I asked my question, and it took in the context of the earlier part of the dialogue. Now, why am I emphasizing that? Since we've been playing with ChatGPT for almost a year now, that kind of seems like, sure, of course, that's the way it works. But I'll tell you, I spent a little bit of time working in AI on the Alexa side, and transferring context from one invocation to the next can actually be tricky. And I'll show you the approach that ChatGPT and that the OpenAI APIs used in this particular case in just a moment. So it's actually quite clever, and it has to do with the way that these AI models work. Now, so this is all running up in the cloud. This is running against that model that has 175 billion parameters, and it needs 700 gigabytes of memory to run. But the whole point here is that I can do these things. I can run these types of models elsewhere. I can run them, for example, on my laptop. So let's take a look at exactly that. So I'm going to jump over here to Postman. Now, what I'll tell you is that I have local AI running on my laptop. And I'll show you in just a little bit about the local AI project and how I was able to get this running on my local laptop. I'll show you that in just a moment. But for now, just know that it's running there. And remember that it's a REST API. So the REST API is right up here. You can see that I'm invoking on localhost 8080. I'm invoking this API. It's version 1, and it's the chat API, and it's specifically the completions API. Now, you'll see what completions means in just a moment. I've already loaded up my initial query, which is what characterizes Impressionist art, and I'm going to go ahead and click send on that. So this is just issuing that REST request, that HTTP request to my local endpoint. And in just a moment, I should get back the response. Of course, when I executed this before I was running Zoom. It didn't take quite as long, but we'll manage. So what you can see here is the response. And in fact, let me scroll this up just a little bit. And you can see that there's some, it comes back in JSON. And right inside here is the content. Impressionist artists are characterized by their use of light and color, etc. Now, the first thing that you'll notice, excuse me, is that this response isn't quite as complete. It has the high points, but it's not quite as complete as what we saw in ChatGPT. So I might want to follow up and say, well, who are some of the famous artists? Who are some of the famous Impressionist artists? So how do I do that? Remember, I emphasized just a bit ago that there was this thing about context, right? Well, the way that I do that is I just add to the query. So the way that I add to the query is I'm going to grab this message. Notice here in the original query, it said messages. And in the response, it says message. Interesting. So I'm going to grab this message. And what I'm doing here, very clunky with cut and paste, I'm doing this intentionally because I want you to see the cutting and pasting, how this query, the subsequent queries are actually crafted, is that I am putting the response inside of my subsequent request. So remember context? So that text, that answer now becomes part of the context for my follow-on question. So now my follow-on question, and you can see that these things are annotated with the role. So the user is myself, the assistant is what came back. I'm going to go ahead and add another part to my questions and say, well, who are some of the famous ones? And see what it comes up with. So we'll go ahead and hit send. So again, what you can see here is that I have just taken the context, and this is exactly what the ChatGPT web page does. It takes the answer that it gave you, it adds it to the initial question, and then adds in your next question that you ask as a follow-up. Now, why is this relevant? Why does this make sense as an API? I mentioned that there's a number of different ways, different APIs that you could have created. And that is because these large language models are implemented as something that are called transformers. What they're doing is they're transforming some language input into some language output. Now, those transformations could be things like a translation or a number of other things. But in this particular case, I'll draw your attention to the completions endpoint. What we're saying here is, let me give you some text, and I'd like you to complete this text. So all of that text, the initial question, what characterizes Impressionist art, the initial answer, and then my follow-on question, you can just think of that as a string of characters. And what we're doing here with the API is we're asking it to complete this. And that transformer is executing that particular thing. So it's looking at all of the characters that came before, and it's running it through its inferencing engine, which we'll look at in just a moment. And then it's getting the output. So here you can see some of the famous Impressionist artists include Claude Monet, et cetera, et cetera. So I'm going to ask one more question because I want to ask about Van Gogh. So let's see. I'm going to again grab this latest message, and I'm going to add it to this context. And then I am going to ask my next question. Suppose I could have done a better job preparing some of these cut and pastings, but if you'll just bear with me a moment, I'll say, what about Van Gogh? And click send on that. Now, this is going to take just a moment. And so again, the transformer architecture is just completing this. And we'll see. Now, you'll notice that with each subsequent request, it's taking just a little bit longer to complete. And that's because it has more input. What it's effectively doing is pattern matching. So it's taking that long string of characters and it's doing pattern matches against all of the content that was used to train this particular model. Now, for those of you who are computer scientists, I'm sure in your classes, you had classes where you did searches and you were searching for words and you talked about order n and order n squared and all of these types of things. It's not doing the pattern matching that way. It's using AI techniques to do that pattern matching, using statistical AI techniques. And I'll talk a little bit more about that in just a moment. So here you can see that we got an answer that says, nope, sorry, Van Gogh is not an Impressionist artist. He's post-Impressionist. So again, you can see that it's able to answer those questions. However, you could see probably some subtle differences in the level of fidelity. The larger model that's running in the cloud is maybe coming up with slightly better or richer answers to the questions that were asked than the smaller model can. All right, with that, I'm going to return back to my slides. So let's go ahead and come back here and let's do exactly what I promised. And that is, we're going to take this particular thing and we're going to dig into that large language model box. So how does that work? I talked about this context that's coming in. I talked about these 175 billion parameters. What does all that mean? Well, that running large language model really has two fundamental pieces to it. It has what's called an inferencing engine. And this inferencing engine does a whole bunch of matrix math. So remember a moment ago, I said that we're not doing like a character by character comparison or anything like that. What has happened here is that the AI technology that's being used is a neural network. It is a network of nodes that are highly interconnected. And so here's just a small kind of visual depiction of that. We have lots of nodes that are highly interconnected. And basically, we're doing a whole bunch of matrix math along these things. What you see here is the inputs are those x's on the left-hand side, and the outputs are the y's coming out on the right-hand side. And again, you can see summations and functions. And again, those are the innards of the neural network. Now, that neural network, that code actually that does that matrix math, it's actually not that big. I looked inside of one of the models, in fact, the Llama model that I was showing you just a moment ago, and it's, I don't know, 7,500 lines of code or something like that. These inferencing engines are usually implemented in high-performance languages like C++ or Rust. And the size of the code, again, isn't that big. And so when you compile it down to that, it's not particularly massive. However, the inputs to that are all of the weights. It's all of the things, it's all of the values that are going into that matrix math. So each one of those gray bubbles that you see in the bottom right-hand corner, there's a whole bunch of values that are coming in. Where are those values coming in from? Well, they're coming in from the model. So I was calling this a large language model, but it's actually the model itself is the input into the inferencing engine. The inferencing engine is the thing that does the compute, but what's it computing on? Well, it's computing on the model. Now, models have various things. They have a set of metadata. They have what are called hyperparameters, which are things like the things that can configure the inferencing engine, for example. They also include a vocabulary. So is this a model that processes English, or is it a model that processes, say, Spanish? So it has a vocabulary. And then it has the weights, or also known as the parameters. And that's when we say that the ChatGPT 3.5 has 175 billion parameters, or that the Llama model has 7 billion parameters. Those are all the weights that are input into this inferencing engine. So you can see that it's not only I have to bring all of these values in, but then, of course, if I have lots more values, then the for loops that are running all of these different layers inside of the neural network are going to have much larger loops, and it's going to take more time to process. So it needs more processing power. The thing to point out here is that those weights form the vast majority of the size of the model, is the weights themselves. Now, where do those weights come from? Well, those weights are calculated during the training process. So the training process is also very compute intensive, not as compute intensive as inference, because inference is just taking those numbers and performing a bunch of matrix math. What is happening during model training period is that we're taking a whole bunch of input and looking at the patterns that are in that input and searching a bunch of different ways of characterizing those patterns. We start with some stabs in the dark on statistical values, and then we adjust those until we reach some level of convergence. So that's the basics of what it looks like from a model perspective. Now, let's circle back to local AI. So what is local AI doing? So again, I've said here, language models, not large language models. Again, I don't want to debate whether we call it a large language model or not. But when it comes to local AI, what local AI has done for you is sitting behind that OpenAI API. It's making calls back to what? Well, it's making calls back to this system that local AI puts together that allows you to load a number of different models. And I'll show you this. I'll go back to my demo in just a second. I'll show you that you can load a number of different models. And then it also bundles in a number of different inferencing engines. So there is some level of standard. And if you remember at the top of the presentation, I talked about GGML, which is this file format. It's a format for these models. It actually turns out that GGML has now been deprecated, and there's a new version of that file format. I don't remember the acronym off the top of my head, but I'll put some of that in the show notes to clarify. So again, it allows you to load a number of different models, but those models are sometimes require a specific inferencing engine. And so when it comes time, and I'll tell you that I learned all of this a few months ago when I first started learning about local AI and the way that these inferencing engines worked and so on. In sorting through and figuring out which models need which inferencing engines and what are the inferencing engines that are available and what are the licenses against those, et cetera, that was all fairly complicated. And so that is one of the big things that local AI does for you, is it brings in all of those different inferencing engines, and it automatically detects how which models are executable in which inferencing engines, and it does that for you. And I'll go into that in just a little bit more detail. But speaking of the models, I just want to show you, and these are screenshots taken from the local AI website, just the list of models that are supported. So remember, this is the upper part of the diagram. So these are all models that are in mostly this GGML format. There might be a few other formats as well. And those are the things that carry the hyperparameters and the vocabulary and the parameters themselves. So these are all the different models that are available. And then this table also shows you which different API endpoints this can be the back end for. So for example, there are some, you can see there that there's a column that says completion chat endpoint. So that first column of models all support that chat endpoint. So that completion API that we saw. But this next one, there's, for example, Whisper does things with audio, not with text. And so it doesn't support the completion API. And so local AI will stitch all those things together for you. So that's in essence the core of what local AI does for you. But that's just the sexy part. So that is like, hey, it'll do the model inference for you. It'll load up the models and it'll execute these inferencing engines. But it actually does a fair bit more. It does a whole bit of, quite a bit of chopping wood and carrying water, as we like to say in this industry. So if this is where we were, this is what we've talked about so far with local AI, is that it has the OpenAI API endpoint and it has these different inferencing engines. Now you'll notice that those I've colored both in blue. The green things are not part of local AI. You shouldn't think of the models as part of local AI. Local AI is about all the tooling that's allowing you to bring your own models, or these models that it has compatibility for, bringing those models into the environment and then being able to execute those. So again, those models are input. And you'll notice that there's multiple inferencing engines. Local AI also has what I'm calling here loosely an ML inferencing framework. So this is the thing that, for example, selects the best inferencing engine for the model that you invoked. And it translates from the OpenAI API into the protocols that are required by those inferencing engines. So those inferencing engines don't have a REST API. They don't have a completion endpoint. And what we've done here is we've said, okay, well, the API for local AI is the completion endpoint. How do we translate that to invoking the inferencing engine with the right model as input? So it does a lot of that kind of mediation for you from the API to the back end executing. It also gives you some model management. It's pretty lightweight, but it does allow you to load models in a directory. And then when you start up the process, it will load those models from that location in memory. So it does give you a little bit of lightweight model management. Model management, by the way, if you're going to be doing anything in production, is incredibly critical to get right, because you need to be able to do things like version models and ensure that you are tying your model version to the observability of the results that are coming from a particular model. So model management, local AI does some lightweight stuff, but if you were to do something like this in a prod environment, you would need more around the model management capabilities as well. And then, of course, it also does some testing. So it has some automated tests that are running and making sure that the smoke tests, the normal tests, everything is executing as normal, even as these inferencing engines are sometimes revved themselves. They're evolved. It does testing to make sure that everything's working end to end. And then, very importantly, it also provides you instructions or a number of different tools to help you from an installation perspective. Now, what did I use here in these demos? What I used is Docker. So I'm just running this as a Docker container. So local AI includes a Docker file, and it allows you to do a Docker compose. That's exactly what I did to start this up. It built everything, and then it made the endpoint available on my local host. There's also instructions for running it locally, so not inside of a Docker container, but locally on a particular machine. And there's also instructions, and there's a Helm chart for installing local AI on your Kubernetes environment as well. So before jumping into the final part of my presentation, I just want to go back over to Postman and show you one other API. So I'll draw your attention now that we've talked about models, is that notice here that as a part of the request, I was including the model that we're running. I'm running a GPT-4all. And by the way, it bears mention that GPT-4all actually has nothing to do with GPT-4, which is the large language model that is the next release after GPT 3.5 from OpenAI. So that is just, we've overloaded the name here. It is literally GPT-4 all. It's intended to say, hey, this is democratizing GPT. So this is the model that I'm running. But what you can see over here is that there's another endpoint that I can run, which says, well, what models have I loaded? Remember, I talked about model management. In my particular running environment, I'm running a couple of different models. I've loaded up GGML, GPT-4all, and I've also loaded up this Koala model. So that gives you a flavor of what's going on with that. Now, with all of that knowledge, let's now go back and do what I promised you from the very beginning. Oh, sorry, I'm going to rebuild that. Is that we're going to talk about use cases. And given that Many of us live in this environment where Kubernetes is looming large in what we do on a day-to-day basis. And that's certainly what I do working for Spectro Cloud, which has a Kubernetes management platform, multi-cluster, multi-cloud, at-scale management platform. Many of these use cases that I'm going to talk about are related to Kubernetes. So let's talk about Kubernetes-related use cases. And there's 3 that I want to talk about. First of all, Kubernetes is hard. Even though we've made great strides and we have many, many tools, and we like to think that we have created some of the better ones for that, it still is hard. When something does go wrong, how do you diagnose what's going on? Or even if things are going well, how do you ensure that you understand why things are going well? Well, it turns out that obviously, like any other platform, Kubernetes generates a lot of log files. And what you can do is we can actually use those log files to train a model. And those log files are input. And then from training that model, we get a set of weights. And then we can ask questions specifically against that model that relate to Kubernetes. So we might ask, why do I keep getting a crash over here? Why does node 5 keep crashing? And it should be able to answer some of those questions. Now, there is a project called Kate's GPT, which is doing exactly that. And there is a PR, and in fact, I'm not even sure, it might have been merged by now, but there's a PR that says, well, instead of using ChatGPT, instead of using the OpenAI endpoint up in the cloud to power this Kate's GPT, you can give it a local AI endpoint and use local AI for inference instead. So there is a PR inside of the Kate's GPT project. And like I said, it might very well have been merged by this point. Also, I'll put this in the show notes as well. There's a blog from my colleague Tyler that talks specifically about Kate's GPT, gives you a lot more details about what I just summarized at a high level. Now, the second thing that I want to talk about is, remember when I was showing you the completion API and how I was taking the answer and making that part of the context and then adding my next question? Well, every one of those inputs, every time I ask a question of ChatGPT using the website or using the API, that question becomes part of the base of values that are used to train the model. So if you have some domain that is quite private, where you don't even want your questions, where your questions actually, having those questions become part of the knowledge base that is powering those answers, if you don't want your data to become part of the training set, then you simply cannot use ChatGPT up in the cloud. It is a data privacy thing. And we are talking to a fair number of customers who fall into this category, who are saying, you know what, it's fine to ask about Impressionist art, but when I start asking questions about the inner workings of my particular product, I want to be able to power my documentation site in a more, use chat to interface with my documentation. But I don't want my documentation, it's not public. I don't want that to become part of the knowledge base. So there are plenty of those scenarios. And then finally, I want to talk a little bit about edge. As it turns out, Gartner has made a prediction that by the year 2027, so not too far from now, we're almost to 2024, 65% of the workloads that are running at the edge are going to be AI-related workloads. So whether this is a loyalty application that recognizes somebody when they walk into a coffee shop, or it is a kiosk that's in a retail, a large, let's say, home improvement place, where you want to ask questions of, about the project that you're working on, which is very much a ChatGPT type of scenario. You, in many cases, don't want to pay Well, you're going to pay a lot of things if you send those things up to the cloud. In addition to the security concerns that we talked about in just a moment, you're going to pay latency costs. You're also going to pay for bandwidth. So anytime any content that is uploaded into into, let's say, a running service in your cloud of choice, AWS, GCP, Azure, any of those, you're going to pay for bandwidth for the values going in and out of that. And by the way, it's probably okay if I'm standing in a home improvement place and I'm asking of the kiosks, I'm probably not going to ask whether Van Gogh is an impressionist artist. So we can constrain the domain. We can shrink the models that are required to run in these edge locations. So remember that in smaller compute environments, we don't have as many resources, so our models need to be smaller. But you know what? In a lot of those settings, a more constrained domain and a more constrained model is perfectly acceptable. So with that, I would like to thank you for your attention. I hope that this session gave you a little bit of an overview of not only local AI, but the way that these types of AI applications are structured and the way that models are created. And most importantly, what we talked about here is the way that those models are executed. And we wrapped up with a few examples of use cases where this might be valuable. So once again, thank you for your attention, and please do reach out to me if you have any questions. Really appreciate it.